All right. Let's talk a little bit about division first before we talk about matrix division. So, what do I call this? Matrix division. The question is, what might it mean to divide by a matrix? Now, Eddie, you have read ahead.
A little bit.
Try to resist answering all the questions. Let's start with number division. If I say something like 5x equals 10, what do you do to work out what x is?
Divide both sides by 5.
Divide both sides by 5. Okay, but I'm going to write it a little bit differently. I want to divide by 5, right? But I could also just as easily multiply both sides by 1/5, right? Because then, well, tell me what 1/5 times 5 is.
1.
1. And 10 times a fifth is 2. And I wrote it that way very specifically because we're going to come up with a matrix that's the matrix equivalent of 1. Suppose I have a matrix, let me think about this. Suppose I have a matrix, maybe we should just do 2 by 2 instead of 3 by 3. Let's start with 2 by 2. 6, -2, 1/2. And I want to multiply this by some 2 by 2 matrix in order to get itself back. What matrix can I multiply it by to get the same matrix back? It's a little bit tricky. But look what happens if I use this matrix. Look carefully about what this is doing. 1 times 6 plus 0. 1 times -2 plus 0. And the second row, 0 plus 1, 0 plus 1/2. What happened? I got the same matrix back again. This matrix is the identity matrix. It's the 2 by 2 identity matrix. How did that work? How come that matrix gave me back the original one I started with? Can you describe what's happening when I multiply by that matrix? Even you can have a go at this one if you want, Eddie.
Well, maybe. It's just cancelling out the other values that aren't needed, and then it's not changing.
And getting only one, that's right, and getting only one of the other. So if I'm multiplying along this row, I'm going to choose the first entry only, which means I'm going to get the first one in this column, and the first one in this column. And on the second row, I'm going to get the second element of the column. It's kind of selecting the first and ignoring the second, ignoring the first and selecting the second. That's how that works. So suppose I had a 3 by 3. I'm going to select the first, then select the second, then select the third. And that's my 3 by 3 identity matrix. And so on, and so that's how you build the identity matrix. But 1's down the diagonal and 0's everywhere else. We are only going to talk about, it's not really division, but what we're doing here with matrices, we're only going to ever talk about this kind of matrix division and identity matrices and inverse matrices and determinants. We're only going to talk about it for square matrices. There are some special cases where you might find 2 non-square matrices that multiply into identity. They are very special cases. They're not a general thing. Remember, in general, I can't just multiply any 2 matrices. So we're only going to be talking about square matrices for this kind of thing. That's a 2 by 2 identity, that's a 3. I don't want to write identity every time, or this matrix every time, so I write I. If I want to be really clear, I could write I3. But most of the time, we'll just write I, and the context will tell us the size of identity matrix we're talking about. Why do I want this? I want to be able to find another matrix that multiplies by my matrix to get an identity, because then I can do some fancy algebra with matrices. Effectively, I'm dividing. So, let me do this. Suppose I have a matrix. Do I want to use M or use A? The book uses A, let's use A. Suppose I have a matrix A, B, C, D. Notice the name of the matrix is a capital A. The elements are little letters because they're scalars inside the matrix. We don't usually put matrices inside matrices, although occasionally we would. Gaussian elimination is one example. I want to find another matrix that when I multiply by it will give me the identity. So I want to work out, I want an inverse matrix. See, I could have written this 5, 1/5 is the same as 5 to the negative 1, right? So I'm going to take this notation and write it here to mean the inverse. I want a matrix here, and I'm going to use EFGH. No, they use PQRS. I'll do the same as the textbook. PQRS, such that A to the minus 1 times A is the identity. Actually,
Does that order matter?
sorry, A to the minus 1. It doesn't matter as it turns out. In general, matrix multiplication you can't swap around, but the inverse you can put on either side, and that is important, as we'll see. It doesn't matter which order we write this. When I multiply them, I want to be able to get the identity. So let's do this. I want P, Q, R, S, A, B, C, D to equal 1, 0, 0, 1. Now, the syllabus just says define and use identity and inverse and calculate determinants and inverses and things. It doesn't say you have to be able to determine this whole process to work out the rule. But I'm going to show you because this is specialist maths and we liked abstract algebra, right? Olivia doesn't look convinced. Okay, what happens if I multiply these matrices? Have a go and then I'll do it. Whoops. 1, 0, 0, 1. Have a go at doing that multiplication. You'll get something, something plus something, something in each of those 4 spots. There's the first one if you're stuck. Doesn't matter which order you put these things in, I'm just going in alphabetic order. It doesn't really matter. BP plus DQ. Check yours against mine. Do we agree? Andy, you okay?
Yeah.
Yours right? Rain, you agree with me?
Yeah.
Okay. If these matrices are equal, then each of these components must be equal. AP plus CQ is 1. BP plus DQ is 0. AR plus CS is 0. BR plus DS is 1. Now it is easy to get confused here, but what you have to keep in mind is I know what A, B, C and D are, and I want to work out what P, Q, R and S are. So if I treat A, B, C and D as known things, I'm left with 4 equations with 4 unknowns. This can be solved. Have a go. Do you need me to give you a hint?
Can we use GC?
No, I don't think it can.
Oh, it'll give some like random values. It'll say like this is some multiple of this and this is.
Yeah, I'm not sure you can do this algebraically.
Alright.
What we do is, hold on. How do I do this? If I multiply this by, how do they do that? So, let me try this. P and Q, because they did P and R, yes, okay. So, B times 1 will give me ABP plus BCQ equals B, and A times 2 will give me ABP plus ADQ equals 0. If I then subtract them, I can eliminate P. Yes, you tend to, I'm really stretching what you learned about simultaneous equations, right? If I subtract those, that goes away. BCQ minus ADQ equals B. Remember, A and B and C and D are known. Which means, BC minus AD, that's what I want to see, Q equals B, and Q is B over BC minus AD. And I have one of the things I didn't know in terms of the 4 things I already knew. Am I pushing your algebra skills a bit too far, year 10s? You weren't quite warmed up for this? Again, you don't have to be able to do this, I'm just trying to make sure I can convince you. Do you believe this, based on this algebra? If I do the others, you end up with, we should get the same results as they did. We did. You can get P is and R and S the same way. I'm going to get this right. S is A over. Actually, I'm going to write it down the bottom for a reason. I'll show you in a minute. And R is A, B, C, C over BC minus AD. I can show you the full derivation of all of them if you want, but given the slightly scared faces I just got from most of the year 10s, this is absolutely some algebra you need to be able to do within about 4 or 5 months. But if you just pick different pairs, or in fact now you've got a Q, if you're really game, you can plug the Q back into here and solve for P. Either way you'll get there. Notice what's on the bottom of these fractions. This is the negative of that. That's why I wrote them in that order. So this is what we do. We actually go, we define, the determinant of A, which we write as delta A, or mod A, or det A. And we say it is AD minus BC. That's this thing on the bottom here. Notice the determinant is the thing on the bottom, it's not 1 over it. The determinant is AD minus BC. So you just get your matrix and you go AD minus BC, that's my determinant. And then we go, then I'm going to leave a space after my then, that's important, I'm going to write something else here. A to the minus 1 is 1 over the determinant times, now what's in the top corner? Top corner was P, so that's D. What's here is Q, and Q is actually it's negative B. Because I've changed this, I've swapped around the sign of what's on the bottom. What's here, that's R, which is negative C. And what's here, that's S, which is A. Now, if you don't like writing det A, you can write mod A, or you can write triangle A. It's up to you. And I have found a matrix which is the inverse of my original matrix. What you absolutely have to know is what the determinant is and how to work out the inverse for a 2 by 2. If it is bigger than 2 by 2, you will use your calculator, according to the syllabus. Okay, almost finished. There is a problem. Don't write this yet. What's the determinant of this matrix? I know, that one's alright. I've got no numbers in the wrong place. That's better. What's the determinant of this matrix?
0.
0. 4 take 4. And then I'm going to be dividing by 0. So, I have to go, if the determinant is not 0, then that's my inverse. If the determinant is 0, there is no inverse, which is exactly the same as numbers. I can't find the inverse of 0. I can't divide by 0. If the determinant is 0, there's no inverse. Let's try it for something other than a weird 0 case. Do I just make one up? I guess I can, right? what is the inverse of that matrix? Power of -1 as a symbol for inverse. Well, first work out the determinant. Let me give this a name. Let's just do it this way. No, I better give it a name. Let me write this differently. E.g. A equals, and I'm going to go. The determinant of A is AD minus BC. (12 plus 4 is 16. Am I going too fast? You keeping up? Then the inverse, that was a bit messy. The inverse is 1 over 16. Now what do? I swap A and D for 3. And I change the signs of B and C. -1, 4. You right, Ryan?
I don't really know what's going on.
What's going on is I'm about to test that if I multiply this by this, I should get the identity.
Yeah.
Let's try it. It's a magic rule. This is the magic rule that gives me an identity matrix in 2 by 2. Let's prove it. Check. A times A to the -1 is 3, 1, -4, 4 times 1/16, 4, -1, 4, 3. I can't change the order of this, but I can move the scalar out the front, so I'll do that later. 3, 1, -4, 4, 4, -1, 4, 3. I'm running out of room. I should go up. There's all this mess at the top, which is 1/16 of. Am I going too fast? I'll wait for you to catch up. 12 plus 4. Oh, look at that. -3 plus 3. Oh, that's what I wanted. -16 plus 16. 4 plus 12. And I'm going to get 16, 0, 0, 16, which is 1, 0, 0, 1. It worked. So this magic rule, work out the determinant, swap A and D, change the signs on B and C, is going to give you a matrix that multiplies with the original to get the identity. Do you want some practice with this before we apply it? Okay, that was my guess. If you have a matrix whose determinant is 0, we call that singular, just because you'll see that word, right? Singular means determinant is 0. And non-singular means it has an inverse. You can try exercise 8.3 and you can go You'll need your calculator for the 3 by 3s. And you can go up to question 12. But the first couple are really boring. You don't have to do question 1 if you don't want to.